The most amazing thing about our universe is its size. How unimaginably big this universe is. But this is also the most disappointing thing. Think about it. If today we use our powerful telescopes to find another planet like Earth in a galaxy which is habitable for humans, it will take centuries to reach there. In fact, it is impossible for any individual to leave this galaxy. Now, everyone knows that the Earth is in the Milky Way galaxy, and the closest galaxy to the Milky Way is the Andromeda galaxy, approximately 2.5 million light-years away from the Earth. So if we use a spacecraft to reach there, the usual speed of a spacecraft is 28,000 kilometers per hour. It will take 94.5 billion years to reach there at this speed. Not only that, if we make a technology to travel at the speed of light, it will still take 2.5 million years to reach there. This is really disappointing. After all, what is the point of exploring all these planets when we will never be able to travel there? But if there is a shortcut to travel outside the galaxy, a shortcut through which we can cover this journey of 1 million light-years in just a few months, then these things definitely become interesting. These are shortcuts. The 2014 film Interstellar, my favorite space film. I would like to mention it again here. In this film, it is shown that Cooper and his team, when they leave Earth in search of more habitable planets, in search of planets like Earth, they travel to another galaxy. From their galaxy to another galaxy, they reach through a wormhole in just a few minutes. This is the scene of the film when Cooper's team passes through a wormhole. According to the film, this wormhole was discovered near Saturn's orbit by NASA. It is mentioned many times in the film because it plays an important role in the film's plot. But the most interesting thing is that this concept of wormholes is not a science fiction. In fact, it is based on real science. What are wormholes exactly, and how can we use them? Before understanding all this, we have to come back to Einstein's theory of relativity. When Albert Einstein wrote his theory of relativity, it was written in a set of equations. The set of equations is called Einstein's field equations. It was revealed publicly for the first time on the 25th of November 1915, when Einstein submitted his paper to the Prussian Academy of Sciences in Berlin, Germany. In total, these field equations are made up of 10 different equations, 10 nonlinear partial differential equations. But they can also be represented by one equation in short. And that one equation looks something like this. Because there is a lot of complexity in this one equation. If you expand this one equation, you can see the steps. Even if you love maths, your head will start spinning after seeing this. These equations roughly tell us how matter and energy influence the curvature of space-time. Albert Einstein had said that to visualize this, imagine a big mesh. When you place objects on this mesh, it bends down due to gravity. The mesh of space-time also bends in the same way. It curves due to the gravity of big planets and stars. The more the gravitational force of a planetary object, the more the mesh of space-time will curve around it. Interestingly, Albert Einstein couldn't solve his field equations by himself. He only came up with an approximate solution of his equation in a specific case. The first person to solve these field equations was Karl Schwarzschild in 1916. He calculated exactly how much the curve of space-time bends in the case of a single ball of mass. This was the solution of Karl Schwarzschild, which helped scientists understand the concept of singularity. What will happen if this mass becomes infinitely dense? The curvature of space-time will wrap around it so tightly that this region will be completely pinched off from the rest of the universe. Because of this, scientists were able to theoretically prove the concept of a black hole, and this was done 100 years ago. Actually, it was the first time in 2019 that scientists took a photo of a black hole. So, roughly speaking, a solution of these field equations was black holes. Theoretically, we already knew about the existence of black holes. We already knew about them 100 years before they were discovered. And the thing is, there is another solution of these field equations: wormholes. You might be thinking, How are these two solutions coming out after solving one equation? I would say, remember, there were quadratic equations in school. There are two solutions to those equations. X squared minus 3, x minus 2, x plus 6 equals 0, x equals to 2, and x equals to 3. Both fit. So if you look at Einstein's field equations, they are much more complicated. There can be a lot of solutions in reality. Wormholes is a solution, and its scientific name is Einstein-Rosen bridge. This name comes from Albert Einstein and his assistant Nathan Rosen, who together came up with this solution in 1935. Understanding the wormholes is very easy. It is basically a shortcut that connects the 2 points of space-time. First, I will explain things in 2 dimensions so that it is easy for you to understand. Look at this paper. There are 2 points on this paper, A and B. If you have to go from point A to point B using the shortest route, which route can it be? A direct straight line that connects A and B, right? In 2 dimensions, there can be no shorter route than this, except this straight line, connecting both the points. But if we bend this 2-dimensional mesh in 3 dimensions, then suddenly you will see new routes emerging. I have bent A and B in such a way that now, if you have to choose the shortest route to go from point A to point B, then you can directly use this distance of a few millimeters between A and B. You can use this distance, and if I make a route here between these two, literally, by inserting a pen, then a shortcut route has emerged to go from point A to point B, which is very, very short as compared to this route. The wormholes are also working the same way. In our 3-dimensional world, we think that the shortest route to go from the Milky Way galaxy to the Andromeda galaxy is 2.5 million light-years away. But if our 3-dimensional space is curved in the 4th dimension, if it is bent, then it is possible that a bigger shortcut can emerge. Now, it is very difficult for us to imagine the 4th dimension because we all live in 3 dimensions. But to some extent, you can understand it better if you compare 2 dimensions and 3 dimensions. Let me tell you another example of this. This is the map of the world. Suppose you have to go from Delhi to New York by taking a flight. Then what will be the shortest route of the flight? You will say that from Delhi to New York, by connecting directly to the state line, the flight will pass over Africa. But in reality, this will not be the shortest route because you are thinking in 2 dimensions. The shortest route will actually be from Finland to Sweden, from Iceland to Greenland, and from there to New York. Looking at it in 2 dimensions, it seems like a long route, and there was no need to go from the top. But if you look at it in 3 dimensions, it will seem like it is a very obvious thing. This is the shortest route. In 1957, scientist John Wheeler published a paper on Einstein's Rosen bridges, and he compared it with a similar analogy. He said that there is an apple and an insect is eating that apple, a worm. It travels from one side to the other while eating the apple. Instead of traveling on the surface of the apple, like our aeroplanes travel on the surface of the Earth, around the circumference. By doing this, the worm travels a short distance. In a way, it has taken a shortcut in space-time, and this term was named by Wheeler as wormhole. And this is where the word wormhole originates. When you search the word wormhole on the internet, you find many such diagrams. Basically, the same thing I did with the paper. I connected 2 points through a hole. Here, it is being imagined that there is a mesh of space-time. There is an object on it which has a lot of gravitational force, so much that the curvature of space-time has bent so much that it has come out from the other side. The mesh of space-time has folded on itself, in the same way as I folded the paper, and this wormhole has become a shortcut to travel from one galaxy to another. But in all these visualizations, there is a problem of dimensions. A wormhole has been tried to represent in 2 dimensions. But as I said, wormhole works in 3D to 4D. So in reality, if a wormhole exists, it will look like a spherical ball. There is a very interesting website where you can visualize how wormholes actually look if their existence is proved. It is a ball-like figure, and as you go inside it, you see things curved around you. And if you turn around and look, the Earth is also moving away from you, and everything will look in a circular shape. That is why the wormhole shown in the interstellar film is depicted in a very realistic way. Here, It is important to say that the concept of wormholes is just a theoretical concept for now. It has been theoretically derived as a solution to Einstein's field equations. In movies, it has been tried a lot to be visualized by scientists. Many theories have been made on it, but practically, no one has seen a wormhole till date. Scientists do not know whether wormholes actually exist or not. But if wormholes exist, they will also work as a time machine. Because imagine, in a few minutes, you can travel millions of light years. This means that you have reached there before the light. Even if the light did not reach there, you have basically jumped from one place to another in time. Now, that's a different thing. If wormholes exist, can humans travel through them or not? Many practical problems arise here when we consider wormholes to be true. The first question is, how will the opening of the wormhole be made? We need a very heavy gravitational force. Where will this gravitational force come from? A black hole. Einstein and his assistant Rosen theorized that only black holes can have such a gravitational force that it can open up the internals of wormholes. Everything is attracted to black holes. Everything will be attracted to it and flow through this wormhole. It will flow through this tunnel. But the next question is, what will happen on the other side of this tunnel? If there is a black hole on the other side, there will be no way out of this tunnel. You will be completely trapped inside it. Basically, this wormhole will not be a tunnel to go from one place to another. Instead, it will be a place to trap. Something like this should happen on the other side, which is the opposite of a black hole in every sense. Something that is as powerful as a black hole, but works in the exact opposite way. Instead of attracting things towards itself, it should send things away from itself, so that an exit point can be created. And here, in our story, there is an entry of white holes. Once again, white holes is a concept that has been proven theoretically by Einstein's field equations. Apart from black holes and wormholes, white holes are another solution of these field equations. What are these white holes? Like white is the opposite of black. A white hole will be the opposite of a black hole in every sense. Like in a black hole, no light can escape once it is trapped. In a white hole, no light can enter on the other side. It can only come out. This means that the white hole will look extremely bright. Russian theoretical physicist and cosmologist Igor Novikov was the first person to use the word white hole in 1964. According to scientists, a white hole is basically a time reversal of a black hole. Like the event horizon of a black hole is a point of no return. Once it is crossed, nothing can escape. Similarly, the event horizon is a boundary of no admission. Nothing can go beyond that point. The objects inside the white hole can go outside and interact with the outside world. But nothing can come back inside. Even though Einstein's relativity theory is a solution, no one knows how white holes will form in reality. Some scientists believe that when the Big Bang happened and the beginning of the universe, at that moment of creation, everything must have emerged from a very big white hole. Another theory is based on the idea given by Stephen Hawking. Stephen Hawking said that a black hole will eventually evaporate when radiation will keep leaking from it, until they vanish in a gigantic explosion. But when a black hole evaporates, what will happen to the information and matter inside it? Quantum theory has a fundamental law which states that no information can be lost. It is called the no-hiding theorem. According to the no-hiding theorem, if any information disappears from a system, it will exist somewhere or the other. Theoretically, if all the information is being sucked in, after the black hole vanishes, it will be spitted out. This is likely to happen through a white hole. Based on this argument, many scientists say that a white hole is formed when a black hole dies. But we don't have any substantial information about the death of a black hole. On the other hand, some scientists argue that the existence of a white hole is theoretically impossible because it violates the second law of thermodynamics. As you might have read in school, the second law of thermodynamics states that entropy cannot decrease in any system. Take this paper as an example. If I tear this paper, then, after the paper tears, the entropy increases. It is not possible to rejoin it in the same way. the way a paper shredding machine shreds the paper, which increases the entropy of the paper. In the same way, black holes shred everything in the universe. The black holes swallow all the planets and stars, and only the radiation remains. This increases the entropy in the entire universe. But if you try to imagine that this is happening in reverse, the entropy is decreasing, this is not possible. And if white holes exist, then they will essentially do the same thing. That is why they cannot exist. Despite this, some scientists believe that not only white holes exist, but in the year 2006, scientists saw an image, 14th June 2006. A space satellite named Neil Gehrels' Swift Observatory captured an astronomical event. Scientists saw an explosion of a white light, and it suddenly disappeared. This event was named GRB 060614. It was a gamma-ray burst. Gamma-ray bursts are basically a lot of energetic explosions which are observed in distant galaxies. Usually, these events happen when a black hole swallows a big star. We see very bright explosions, but in this case, no evidence of a star was found. So this hypothesis was made that it was an observation of a white hole. Since then, we have not seen such events again. And that is why white holes are only a theoretical thing. But the thing to note here is that black holes used to be a theoretical thing, but then one day they were practically proved. So it is possible that in the future this will happen with white holes as well. The same thing can be said about wormholes as well. It is possible that in the future they can be proved. But even if their existence is proved, scientists still doubt whether humans will be able to travel through them or not. The most interesting news about the existence of wormholes is from 2015, when scientists created a magnetic wormhole for the first time. Till now we were talking about wormholes in the sense of gravitational force. But if we talk about magnetic force, scientists have already been successful in creating wormholes. What does this mean? There are two ends of a magnet. One is the North Pole and the other is the South Pole. We all know that two ends are always together. Even if you break a magnet into two pieces, the two poles of both the pieces will still remain. What did the scientists achieve by using some special materials? They separated the two poles of the magnets. They created an invisible gap in between. Basically, the magnetic field of one magnet went inside one end of the wormhole and came out from the other end. You can see its visualization here. The image on the left shows a device created by the scientists which separated the two poles of the magnet. This device is basically working as a wormhole for the magnetic field. We can see this device with our eyes, but if you look at the magnetic fields in the right picture, you will see that there is one pole of the magnet on one side and another pole on the other side. Just like a wormhole in space will work to bend the space-time curvature, this wormhole here worked to bend the magnetic field. To create this magnetic wormhole, a high-temperature superconducting material was used. Its name is yttrium barium copper oxide. A liquid nitrogen was later used for this experiment. Finally, friends, I would like to say that even if the existence of wormholes is not proven in the near future, it doesn't mean that we can't find other ways to travel faster than light. Theoretically, many other solutions are proposed. One of them is Alcubierre Drive. It was proposed in 1994 by theoretical physicist Miguel Alcubierre. The idea here is that there will be a spacecraft that can travel at a speed faster than light. But how will it be able to do it? It will be able to do it by contracting the space-time curvature in front and expanding the space-time curvature in the back. Theoretically speaking, another solution of Einstein's field equation is presented here by Alcubierre Drive. It will be interesting to see what other solutions of these field equations are proposed and what practical things can be derived from them.